The GitHub project with the most stars on my profile and one of my best YouTube videos got noticed by an actual data scientist who has a master's degree in natural language processing from NYU, and he also invited me to possibly work on his team and got me an interview at his company. This was the first real opportunity that I got from one of my YouTube videos, and it just blows my mind how important it is to market and share your projects online in order to get these kinds of opportunities in the first place. And given that a lot of the questions they asked me, they straight up just told me during the interview, hey, these are graduate level math and data science questions. This was a really, really cool opportunity just to even interview at my skill level and point in my career. But if you're wondering what questions I got asked, I got 3 interviews. The first one was with HR, just interest-based for the company. The second one was with a manager who happens to be a top Kaggle grandmaster and who also holds a PhD from one of the best universities in Australia. And the third one was the 1.5 hour long technical interview that I'm going to talk about in this video. And the crazy part was that a lot of these questions I did not know the answer to, since they were half of them were mostly not NLP focused questions, which was what the company focused its technologies on, as well as one of my interviewers had his master's degree in natural language processing. So I should have been expecting to get questions like that. And it kind of shows that even if you don't know the answer to things, your interviewers will often care more about your persistence and your thinking rather than percentage of total questions you answered correctly. So just think about that when you interview. The first question was supervised versus unsupervised learning. This is a very basic question. Supervised learning deals with labeled data. Unsupervised deals with unlabeled data. Supervised learning, you train something to predict some class labels or output some continuous value in the case of classification and regression, where you have the output Y labels. In unsupervised learning, it's with unlabeled data, you're trying to make sense of it. You're using clustering, all sorts of different techniques to then learn and gain insights from it. K-fold cross-validation was also an important question they asked. And the idea behind that is you split up your data into K different groups. You take one group and use it as a test set. You take the rest of the data and use it as your training set. And then you want to train your model on that training set and then use that one test set to output its accuracy. And then you want to keep doing that for different parts of the data and keep looping that until you get to all K parts of the data set being test data. And this is really important, especially to create less biased models and also use models where you have limited data to train them on. All right, performance measurements of classification. So this was a really big important one, a fundamental data science, machine learning concept. So the idea is classifiers are kind of much harder to evaluate because with regression and regressors, they output some continuous value. You can just take the difference between your output and your model and the actual output it should be outputting. You can take that difference, you can do all sorts of things. That's pretty easy to do, but classifiers output discrete classes, which you can't really subtract a dog from a cat class. You can't really do that. So what you have to use are different measurements. So one of them is accuracy and precision. One of them is accuracy, which in general, accuracy is how close you are to the real value. There's also precision, which is how many times you can repeat a same output, so how precise your model is. And the confusion matrix right here is going to be something that tells you how many times the classifier classifies whatever you're doing incorrectly. So in this specific one right here, you have the true class and then the predicted class right here. So your accuracy is going to be your ratio of correct predictions to all predictions. It's going to be your true positive plus your true negative. So basically the diagonal divided by everything else. So you take the identity diagonal and then you divide it by the sum of everything else. That's what you get your accuracy from. With skewed data sets, however, this can lead to a false sense of performance because at that point, you're just guessing by probability. Like for MNIST digits, I'm pretty sure the data set is split into 10% of each digit. So the model can learn to just randomly guess or just guess 10% of the time the correct digit instead of actually learning it. So accuracy by itself, especially with limited data, is often not a good measurement. It can be helpful, but I think what's more important to use is precision and recall. Precision is the accuracy of your positive predictions. And what it means is when your model claims a class is classified as this one class, it is correct only blank percent of the time. It's precise is that percentage, which is the true positive divided by the true positive plus the false positive as well. And this is kind of the positive row right here is what I call it based on the predicted class, that circle right there. And then recall is going to be your rate of true positives, which is the ratio of correctly detected positive instances. So you kind of take a look at the positive column in your true class, and that's the numbers you're working with. So your true positive divided by your false positive plus your true positive divided by your true positive plus your false negative. So your model detects blank percent of the classes. There's also your F1 score, which is the harmonic average of precision and recall, which gives more weight to lower values because you want it to only be high if both precision and recall are high. But there's often a trade-off between deciding whether you want less false positive but more false negatives, which is highly precise, or less false negatives but more false positive, which is high recall models. There is also the receiver operating characteristic, which you're basically graphing recall against the false positive rate. And then you can graph this, and with this graph, you want to find the area under the curve. And that kind of gives you another measurement. In addition to precision and recall percentages, this area kind of gives you how good your model is as well. And you want it to be as close to 1 as possible, where 0.5 is going to be your just a random guess. And you typically want to use the precision recall curve when you care about having fewer false positives or when the false positive class is not a lot. Otherwise, just use the ROC AUC curve as well. So I've also forgot you can graph precision versus recall, and you'll tend to see that the graphs are inverses of each other and that there is a trade-off between them oftenly. So you just pick which one is used for whichever case you're using. Then there was the natural language processing question. So what is an embedding vector? The way I described it, it was a vector space that groups similar words. I didn't describe it like that. It was a vector. What it is a vector space of words that groups together similar words, and that also tells you the distance between each word, just tells you how similar they are. And you can have different spaces that do different things like male to female, verb tense, country capital, and that's an embedding vector right there. The next question I got asked was the difference between BERT and GPT-3 in terms of them both being pre-trained large-scale transformers. So what's the difference between them? Well, the difference is that BERT is an encoder while GPT-3 is a decoder. What BERT does is it's trained at first to learn language, just English in general. And how it does is you give it sentences with masks in them. So you randomly place some blanks within the sentence and BERT tries to fill in the blanks. Then that's why it's bidirectional encoding. And that's how BERT is trained. Meanwhile, GPT-3 is a decoder. It's about 470 times larger, and it generates a new sequence as its decoder. And it's first trained performing a bunch of different NLP tasks, and then uses few-shot learning to kind of specify and fine-tune the model into one specific task. And it's better if you don't have a lot of data and you want a different or broad range of tasks you want to perform as you fine-tune to doing your one specific task. That's the whole idea behind Codex. So it being able to generate code doing a bunch of other things. There's a lot of different tasks you can do. So that's why GPT-3 would be used in that case. The next question I got asked was a problem where, given a directory of different recipes in text form, they wanted me to design a data pipeline and model system that outputs a given recipe and classifies it based on its country of origin. And then the question was describing in detail how the data preprocessing worked. So text apparently can be normalized just as much as continuous data. And the way you do this is you can make text lowercase, remove punctuation and non-Unicode characters if they're in different languages. Just remove edge cases that would make the data weird so that it's just all lowercase English. And then you want to encode the recipe text into vector embeddings, the vector embeddings we talked about earlier. And I think the correct answer was using a self-attention transformer. There's no really correct answer, but I think the way they wanted to do it, the way they would do it is using a self-attention transformer where you focus kind of on the beginning and ends of the recipes. Because if you think about it, the beginning of a recipe will often be its ingredients. Some ingredients are very specific and only grown in certain countries. The end of the recipe, the way the meal is finished, can also be very specifically done to different countries. So kind of focusing on them as well, as opposed to focusing on everything, because the steps at which you make it may not be as relevant, or they could be, but that's why you would use attention there. And the last question I got asked was how would you embed an entire document and just put it all into one vector? So there's two different ways of doing it. I said something about the dot product, which was kind of right, but the way they wanted me to do it was encoding the embedding for each word, and you make a vector for each word in the document, and then you aggregate them somehow using not the dot, but the Hadamard product, which is the dot product, but you don't add up the things in the end. You keep the summed components parts, so it outputs like a vector as well. You can also use another technique, which is a bag of words. So basically you take the sentence and you put it into a vector with each different word, and that's another way to do it. But yeah, that was my first data science interview. I hope you found this video interesting and helpful as you prepare and study for your own data science or machine learning interviews. And yeah, that was a really good interview. And yeah, I hope you found this helpful. I'll link the email generator project in the description below. It was honestly a fairly simple project. It was more the idea of, it wasn't really that technically advanced. Like I only used Streamlit and I imported OpenAI, and then the probably most technically advanced part of that project was generating Gmails with a URL, which once you got it to work, it wasn't that hard. It was just string manipulation. But yeah, that was it. Thank you for watching. I hope you found this helpful, and good luck on your future interviews, and hope for the best. See you.